We're starting with a lovely painting of mine again. And today we'll be studying two algorithms. One Prim's algorithm for computing a minimum spanning tree, and one Dijkstra. I hope I'm pronouncing it right. I'm not sure. Just correct me if you have another version which sounds better. Which is basically computing the minimum distance between a node and any other node in a graph. So for today, we will be interested in the weight of our edges, meaning these little things. And that's why I actually put them on my graph. So there's 12, 11, 16, and so on and so forth. Now, does anyone know what a minimum spanning tree is? And can also share it with everyone else.
The distance from the starting node to any other node is the smallest possible for the weight.
Yeah, but it's a bit more than that.
It's a subgraph of the original graph, which contains all the nodes and it is a tree, and the sum of the weights of the edges is minimal.
Yes. So basically, sort of like a subgraph, which spans all the nodes, and it contains a subset of all the edges, such that the weight or the sum of the weight of all the edges is minimum, hence the minimum spanning tree. Okay, so Prim's algorithm is rather simple. And the basic principle, and I want to grab a pseudocode, Prim algorithm pseudocode. This is far too ugly. Oh, well, that's... Well, you know what? Screw this because it's too long. So the main point of Prim's algorithm is that starting from any node, so let's just start off from the first one, A. Okay, wrong color. There we go. We have to span the whole graph, meaning we have to somehow reach all the nodes through minimum edges. And at each step, starting from any of the nodes we already visited, we choose the minimum weighted edge. So if we start from A, we can see that the minimum edge is from A to F, correct? Yeah. Let's just write that here. So it's A, B, C, D, E, F, and G. Okay, so the minimum edge is from A to F, and which is a 6. And we color F as well. Now, from both A and F, we need to find the next edge, which is minimum. So we now have to compare all the edges which point from A to all other nodes adjacent to A, and from F and all other nodes adjacent to F. And which one is that? Tell me. What is the next edge which we have to pick now? The minimum edge from A or F?
FE.
FE, yes, because it's a 4. All right. What comes next?
EC.
EC, because it's a 2, correct. How about next?
CD.
Yes, that's a 3, correct. How about next? We have 2 more nodes which are not covered. So
CG.
CG, yes, that's correct. And how about next?
GB.
GB, yes. Whoa, well, that's okay. There we go. Okay, so That's Prim's algorithm, and now we visited all the nodes, and let's jump into actually implementing it. It's not a big deal, but I have to switch this around. There we go. And now you can see my editor. Is that correct?
Yeah.
Great. Now I've added two files. One is graphalgorithms.h, and this contains two macros, and graphalgorithms.c. And this should include also, I think it should include both this and graph representation.h. We're going to be using basically the same code as last time. So let's write Prim's algorithm. No, not from here. Let's just copy it from here. Okay, and printf Prim's algorithm started. So we have a few variables which we have to initialize. First off is something like number vertices visited, and we'll initialize that with 0, and another one is an I, which is going to be an iterator. And we're also going to be needing a visited array, and we have that, and we can initialize that dynamically. So visited is equal to int malloc size of int times the number of vertices. And remember, this was a global variable you can find in graph.h, and it contains the number of vertices or of nodes, same thing, which can be read from the file, this one here. Okay. And now we have to initialize this visited array. So for I equals 0, I smaller than number of vertices, I plus plus, whoa. Visited of I is equal to unvisited. Formatting, and okay. Now, there is a cost, which I'll also have to compute. So we can actually just add that here, a min cost, which I'll initialize to 0. And we mark the first starting node as visited. Visited of start node is going to be equal to visited. And then there's a simple while loop going on. So the ending condition is that basically I've visited all the nodes. So I already visited one, so I would have to increment number of vertices visited by 1. And then in my while loop, I can write something like this. While number of vertices visited is smaller than number of vertices, I get to do something. Okay. And try to remember what we just previously discussed. We are interested in the minimum edge from our currently visited nodes. So we have this edge structure type, and you can find it in edge.h, and that has a source, destination, and weight. So we can extract one of these types, and let's just name it min edge, and maybe create a method called get minimum edge for currently visited nodes, and we'll pass it as a parameter the visited array. And let's also just create this function. Let's put it, yeah, below, why not? Okay. Now this function will have to iterate through all the neighbors of my visited array and get the one which is the smallest in weight. Okay, let's see how we can do that. First off, let's write two for loops. For int I equals 0, I smaller than number of vertices, I++, and I'll do that again with a j.
In order to obtain the maximum efficiency, shouldn't we use a priority queue here?
We could use a priority queue, but then again, I didn't want to overcomplicate it. Yes, there's an approach in which you can use a priority queue. You can do that at home if you want to. This is the more, well, straightforward approach, I guess. But yes, you are perfectly right.
Okay.
Thank you. Okay, now there's one thing I forgot. This result, the thing I want to return, I'll have to initialize it with, I have to initialize its weight with something like max, because I want to get the minimum, and then I end up comparing each and every one of the other neighboring edges with something like a big value, so I can set it to this one and make sure I don't miss any of them. Okay, so if visited, and these are the conditions which have to be met. So first off, if visited, and this is actually wrong, this should be named something like this. So if visited of I is visited, so if the node the node at this position is marked as visited, and the node at position J is not visited, so this is not visited, or you can just equals unvisited, it doesn't really matter, and the adjacency matrix of I and J is bigger than 0, then I can do something. Now, does everybody understand what I just wrote here? Is there anything unclear as to why I need specifically these 3 conditions? First, I want to make sure that my source node is visited. Then I have to make sure that my destination node is not visited. And then I have to make sure that there is actually an edge between my source node and my destination node, which is represented by I and J in this case. Now, there's another if here. If the adjacency matrix of I and J is smaller than my min edge, my result of weight, then I will do something, and I actually don't like this result here. I would much rather have something like minimum edge. Okay. Well, now I can basically attribute the source of the minimum edge. So source is equal to I. The destination of the minimum edge should be equal to J. And the weight, can anyone tell me what the weight should be?
The value in the adjacency matrix.
Yes, this one over here, exactly. Okay, and at the end of all this, this function will return the next minimum edge. Okay, whatever. All right, now going back to our algorithm, we have to mark the destination of this new edge as visited. So visited of min edge of destination is gonna be equal to visited. And also what I would like to do is to add this min cost, the weight of the new edge to the minimum cost. And I actually want to also print the order in which I found these edges. So allow me to allocate an array called edges, so edge t, edges equals to edge t malloc size of edge t times number of vertices. Yeah, actually I wouldn't need, do I need all of them? Yeah, no, I just need one less, and you'll see why. And here I'll do something like this: edges of number vertices visited plus plus, oops, is equal to minimum edge. Okay, and at the end, I'll write a function which prints all these edges, print edges, and number vertices visited. Oopsie. Okay, and let's create this new function. It's fine. And allow me to just copy this code as to save some time, because it's just printing stuff. Okay, and this is actually a, okay. And here I should just write something like printf, the cost of this minimum spanning tree by Prim's algorithm is this, and that's minimum cost. And also something like printf Prim's algorithm ended. No, come on. Multiple languages, good Lord. Okay. So, any questions so far? No, nothing. Okay, I will then assume that everyone got the gist of it. Let's just run the program and see what we get. And what we get is we get stuck or not. What's going on? Huh. Something happened. It's weird. All right. And now it gets stuck. So I'm guessing that the only reason it should get stuck is this while loop. No, I don't understand why it doesn't print anything before that. Thinking. Could it be? No, okay. So that fixed the problem. Yeah. No, it makes sense, of course. And it cracked because of this and because of this. Yeah. Never mind. All is well now. So let's get back to our result, previous result. It was AF. Let's copy this actually from here and move to the other side. There we go. Oh, come on. Aha. There we go. So our result is A, F, E, C, D, G, and B. And I think it kind of is exactly what you guys found out, or we found out when we ran this algorithm in our head. So we first pick the AF edge and then FE and then EC because it's of weight 2, and then CD, which is 3, and then CG, because it's 7, and finally CB, because that's the last one. Okay. Any questions so far? No, nothing? Come on, guys, tell me something, anything.
Oh, fine.
Okay, so if you're fine, that's perfect then. No break then. Because we're almost done. We have just one more algorithm and that's it for today. By the way, I think we're gonna skip next week's webinar, mostly because we just, besides this lab, we just have 2 more content labs. One is with hash tables and the other one is with sorting algorithms. And that would have been it for this semester. And we would have had like 3 more tests. So at least 5 more weeks, but I don't know what to do with those tests yet. So most likely next week is going to be off, but let's talk about that later on. Okay, now we are left with Dijkstra. And does anyone else pronounce it differently, by the way? Not a rhetorical question. No one, everyone says Dijkstra, because I've heard it in so many ways. Fine. Okay, so can anyone tell me what Dijkstra does?
It returns the shortest path between the source node, the start node, and every other vertex.
Yes. Yes, exactly. And if you run it for of course, if you run it for all the nodes, then you get the shortest path from each node to every other node. But in practice, or in its purpose, I guess, it just returns the shortest path from one node to each and every other node. Okay, so let's start that off. Actually, well, let's look at the pseudo. Should we look at the pseudocode first? Yeah, let's do that actually. And let me take it from somewhere. Yeah, this looks about right. Okay, and I will share my paint again. Okay, can you see this paint thingy?
Yep.
Yeah.
Yes.
All right, so let's see what we have here. Because it might not be exactly what we're going to end up writing, but I think it's close enough. It is, but it's not complete. I don't like this. Maybe this one's better. Slightly. Okay. So we start off from our source node. And first off, we need a few more things here. We need a distances array and a previous array. And that previous array will basically contain the nodes which are previous to the other nodes, and I'll explain a bit later. And we'll need a queue, but actually I think we'll be using a stack, not a queue. Okay, and we initialize, and this distance array will basically contain the distance from our source node to all other nodes, and this will be dynamically updated all the time. Okay. So we add this V, we add all the vertices in a queue. And then while our queue is not empty, we pick, first off, so we always pick the vertex in queue with the minimum distance, yeah, with the minimum distance, I guess. And then we remove U from the queue. And for each neighbor V of U, we compute the distance from U to V. And then we update if that distance is smaller than what we currently have in distance of V. Basically, that's the distance to V. Then we update our distance array here, and previous node will no longer be what was there before, but is gonna be U, because we found a shorter path which comes from U to that node. Whew, good Lord. It's a greedy algorithm. That means that at every step, we will choose what seems to be the best option. Can anyone tell me what is the caveat of a greedy algorithm, and why this greedy approach isn't always the best? Come on, anyone.
You can be sure the result is the best one, but it's fast.
You can or can't be sure?
Can't be sure.
Why? Why can't you be sure?
Maybe you could have taken a better path, but you can't think ahead of. I can't explain.
Okay, but yeah, thinking ahead, that's a good way of picturing it. Now, imagine every algorithm having a space of solutions, and you can imagine that space as being a big list of points in this circle. Okay, so it might not be the best representation, but imagine each one of these points being a possible solution to your algorithm. Okay, and of course there are solutions which are better than others. Okay, and some are called, so the best solution is called a global minima or global maxima, depending on what you're trying to achieve. For example, we are trying to get the shortest distance from a node to each and every other node. So let's say we want the shortest distance from A to G. Okay? Now, there could be a lot of solutions for that. There's one which is the best one, or more in case they're equal in some sense. There's one which is the best one, and in our case, it's probably ABG. I don't know. I can't see a better one from the top of my head. It's probably ABG. But another solution could be ACG, which is a bit higher, because ABG is of weight 14, but ACG is of weight 18, but it's still a solution because I can still reach G. It's not the best one, but it's one solution. Now, greedy algorithms always take the best decision, but without having this global idea in mind. They're not taking the solution which is globally the best, because at every step you might reach the global best solution if at one point you are actually not choosing what seems to be the best solution. So the point of a greedy algorithm is that it picks the best solution with all the data it has at the current step. That might not be the global best solution. In case of Dijkstra, it is, but that's just just one example. You'll have an extra assignment, which is called vertex cover. Now, vertex cover is an interesting problem because it relies on approximate solutions. Actually, it's approximation, the vertex cover approximation, which I asked you to do in the homework, or actually I'll ask you as an extra assignment. Its approximation is a greedy one. And it's greedy because it's actually an approximation because it doesn't reach a global minima or global maxima guaranteed. And another thing to mention here is that we need this approximation in case of the vertex cover problem, which you'll see what it is in the homework, because finding the global minima in that case is actually an NP problem. Can anyone tell me what an NP problem is? And it's written like this.
Problem for which a polynomial time a solution is not known.
Yes, well said. Until now, at least, a solution in polynomial time is not known for that specific problem. And in the case of the vertex cover, well, we don't know a great solution. And non-polynomial solutions like exponential solutions or factorial solutions are in practice unusable. They take way too long. And so we attempt to solve these problems, these really difficult problems, NP problems or NP complete problems, whatever. We attempt to solve them by using approximations. And one of these approximations is the approximation for vertex cover. And this is what your extra assignment homework is going to be. And that, as to close a few parentheses, that approximation is a greedy algorithm. And so is Dijkstra. Dijkstra is more like a greedy combined with dynamic programming. That whatever, doesn't really matter all that much. But yeah, so just remember, greedy algorithms don't always lead to the global maxima or the optimal solution. Let's just leave it at that. Greedy doesn't always lead to optimal.
I have one question.
Yeah, sure.
Regarding the homework that we had for this week, the problem of finding the longest simple path between two nodes was also an NP complete problem, wasn't it?
It was? When?
Okay. Well, how do you mean when?
This was an NP complete problem, finding the best shortest path.
I'm not sure about being NP complete, but it seems to be NP because me at least, I didn't find any polynomial time solution, and I struggled to find anything on the internet.
But Dijkstra is polynomial in time.
But we had to find the longest simple path, and it cannot be done with Dijkstra or Brabant-Ford or anything.
Ah, you mean the homework for today?
Yeah.
Yes, you are right. You're right.
Okay.
Yes, that was also an NP problem. Yeah.
Okay.
Yep. You are perfectly right. Okay. All right. So let's just start implementing this. But I have to end this call. I'll give you a 2-minute break, and we'll be back. Okay. All right. So I wrote a few, like the boring stuff, the initialization already. Basically, I initialized a distances vector, a previous vector, and a visited one. I initialized the distances one with max, which is a high value. It's 9,999. Previous and visited are both marked as undefined completely. And finally, the distances from the start node to basically itself is 0. Okay, now we'll again have a while loop, and the condition is rather similar to Prim's algorithm. While number of vertices visited is smaller than number of vertices, then we'll have to do something. First off, as in the pseudocode, we have to get a u, which is the get minimum distance vertex based on our distances vector, our currently current configuration of the distances vector, and our visited vector. And I wrote this small function here, which basically gets the minimum vertex, which is node, based on my currently visited vectors and the distances I already have computed. Okay, and this gives me u, which is a node, a vertex, right? So then I mark u as being visited. And I now have to fetch all the neighbors of u, and I do that with the code I've written last time. So int number of neighbors of u is get number of neighbors of vertex u. And then the actual neighbors is going to be int neighbors equals to get all neighbors of vertex, and that's u. And for all of these neighbors, so for I equals to 0, I smaller than number of neighbors, I plus plus, I take each one of these neighbors into a w, and this w, of course, is a edge. I'm sorry, it's a vertex. It's a node. And as in the algorithm, I compute the alternative distance. So from u plus the alternative distance of u to w. And here, so what I have here, basically, can anyone tell me what they understand this alternative distance is and what it means? Really? No one? Hello? Guys, can you hear me?
It's a distance which is not completely defined until now. So that node is not part of the Dijkstra tree yet, but it may be one of the smallest distances, and then we will add it to the Dijkstra tree.
Not really. No. Or I didn't understand you properly. So, what is distances of u? Or what does the vector distances actually contain?
The distance from the start node to every other node?
Yes, correct. So then what is distances of u?
The distance from the start node to the node u.
Correct. And what is distances of w?
The distance from the start node to the node w.
Perfect. Now, if I am to find a distance from my start node to w going through u, which is smaller than the distance I already have to w, then I have to do something about it, right? That means that I actually found a route to w which is shorter than what I found before, correct? So assuming, let's just assume we let's assume W, and I'll write this in comments. Let's assume W is equal to 1. Our starting node is equal to 0, and U is equal to 4. Okay. And distances of 0, of course, it's 0. Distances of 1 equals to 20, and distances of 4 is equal to 4, and adjacency matrix of UW, that means of 4, 1 is, or same thing, 1, 4, whatever, 4, 1 is equal to 8. How much is my alt in this case? 12, because it's basically distances of U plus adjacency matrix of UW. Okay. But what does that mean, actually?
That we found the new minimum distance between start and W?
Yes, yes. Because now I can know for a fact that if I go through U, which is an intermittent node, I'm sorry, intermediate node, then I can actually trim down my distance from my starting node to W, because the distance from U to W plus the distance from my start node to U is smaller than what I previously had in distances of W, which is the distance from from my starting node to W. So in this case, I will need to update a few things. First of all, distances of W will be equal to what?
Alt?
Yes. And also my previous array of W will be equal to?
U.
Yes. This previous array contains the nodes I have to go through in order to reach a certain node. So previous to reaching W, in order to find the smallest distance between our start node and W, I have to go through U. And this is applicable for all of the nodes. Okay, and here, number of vertices visited, ++. Now, that's basically it. At this point, I have all the data I need. I just need to print it out in a pretty form. And I'll be doing that in a jiffy. Let's just write for I equals to 0, I smaller than number of vertices, I ++. I initialize U with I. It starts from 0, it doesn't really matter. And if I is different than the start node, oops, then I can do this. I'll be using a stack. I won't be using a queue like in the examples, but it doesn't really matter. And check this out. While previous of U is different from undefined, push U, and U equals to previous of U. And then I will printf path from C to C is this, and I'll need start node plus A, I plus A, and this. And while I don't have an empty stack, oops, I will printf an arrow and peek of the content plus A and pop. Okay, this is just a way of printing all these nodes, all the nodes I have to go through from my start node. And let's just look at how it looks like. Dijkstra of 0, I guess. Go away, go away. Okay. So path from A to B is, simply put, AB. The shortest path from A to C is AEC. And let's double check these things on our graph and make sure they are correct. So I'm gonna share my paint. Did I close it? No, I didn't. There we go. Okay. Now, the shortest path from A to B is AB. So basically, I couldn't find anything else better, and it doesn't look like I could. But a more interesting one is from A to C. So there is a direct path from A to C, which is of cost 11 here. But if I go from A to E, I get the cost of 7. And if I go from E to C, I get the cost 2. That means that the total cost from A to C using this route is actually 9, which is slightly smaller than 11. That's interesting. And from A to G, I go from A, B, and G. That's what we assumed a bit earlier. Let's try something else. Let's try all the shortest paths from node C. Maybe actually D is more interesting, or G, why not? Yeah, G is even more interesting. These are all the shortest paths from G to all other nodes. So the shortest path from G to A is, of course, the shortest path from A to G, and that's GBA. Okay. Going further, maybe from G to E, the shortest path is GCE, and that is GC, which is of weight 7, plus C to E, which is of weight 2. So that's a 9. And yeah, well, basically that's it. That's Dijkstra for you. Do you have any questions so far? No one? Nothing? Really? You are so helpful.
From
Not.
For G, shortest path from G to F, is there an edge from D to F?
Is there an edge from D to F? If not, I probably forgot to put it in. Let's see. Yes, there is one over here, and I forgot to put it in. It's this one, D5.
Oh, okay.
So there we go. Yeah. It was in the adjacency matrix, but I forgot to put it in the graph, and now it makes more sense. Sorry. Good eye, though. Good eye for catching that. Any other questions? Okay, I guess not. For your homework, the mandatory assignment will be implementing Kruskal and Bellman-Ford. Now, Kruskal is another way of computing a minimum spanning tree. It's not much different from Prim. It is a bit of a different approach, but it's quite easy to implement. And then Bellman-Ford is another way of doing Dijkstra. But I'll leave you to it. You'll have to read a bit about them. You'll have to implement the pseudocode. Of course, you can use all the material I just used, and it'll be on Git. And yeah, that's the mandatory assignment. And for the extra credit one, as I said before, you'll have the vertex cover approximation. And that's a very interesting problem. I would really like you all to try it at least. It's very simple to implement. It's a lot easier than implementing the optimal one. You can actually, for a small amount for a small graph, of course, you can try out the optimal one just to see how it behaves, how the approximation behaves compared to the optimal approach. But once you have a big enough graph with enough nodes, then you'll see that the optimal solution, which is not going to be in polynomial time unless you're a genius and find a solution, and then we're all going to probably die in the next few months because of that. And I'm not even kidding. In case, yeah, so the solution, the optimal one is not going to be in polynomial time. And you'll see that if it's a big graph, your computer is going to have a bad time with it. And by the way, the reason why I'm saying that, if you guys find out a polynomial solution to any of these NP problems, that the world is going to go to hell, is that basically all encryption, all internet encryption is based on such NP problems. And it's, I think, integer factorization or something. And in case any one of the NP problems gets a solution in polynomial time, every other NP problem will get a solution in polynomial time. They are all linked. And you'll find that out how they're linked. And maybe if you're going to do master's degree in computer science, that's when things get a bit more interesting, and you'll see how all these issues, all these problems are actually reducible to some more fundamental problems like the 3-SAT and so on. And so yeah, in case you find a solution out, you're a genius and you'll be the richest man on earth in no time. But then we're in deep problem, really. Yeah. But brilliant minds are already on it. So don't despair. Any questions? No, nothing. Oh boy. You're not fun in any way. Okay. Then we're going to have to stop here. If there's anything, feel free to ask around in the group. And if not, just stay safe and have a grand time. Take care.